Alright, I'm going to test this out on a problem we've already done, where we have a collar on a pole at some point A and is going to move down to some point B. It is attached to the wall by a spring with a known spring constant K. The collar has some mass M, and it's going to move some delta Y equal to 1 meter. And in B, the spring will now have some stretch. Initially it does not have stretch. We'll say no initial spring stretch. Is there anything else we need to know about this? Let's find out. I'm going to use the conservation of energy. Let's say T1 plus V1 is equal to T2 plus V2. I'm going to go ahead and write out all the terms. I don't know if we're going to need them, but I know there's some possible gravitational potential, some possible initial velocity. Actually, in this problem it is 0 in this case, but there could be, right? We could have had it moving down with some velocity. In this case it is equal to 0. We are releasing it from rest. And we could also have some initial spring stretch. Call that some x1 squared times k over 2. All of that is going to equal its analogous final state, the gravitational potential at 2, the kinetic energy at 2, and some spring stretch. Okay, so if it had no initial velocity, we can get rid of that term. I'm going to say h is equal to 1, calling here 0, which means in our final state we have no potential energy. It also said no initial spring stretch, so we can get rid of this term. Now we're just left with an mgh plus 1/2, is equal to some 1/2 mv final squared plus 1/2 kx squared. We are done. We have everything. We can solve for v. That would be mgh minus 1/2 kx at 2 squared, all divided by m, and that's all times 2. And then we'd have to take the square root also. And we could simplify that more if we wanted. The only thing we don't know is what was our h or delta y. Well, let's do geometry. We were given that, well, I didn't write it before, but we were given that this was some 0.75 meters. It dropped down some 1 meter, so we can say that this length is equal to the square root of 0.75 squared plus 1 squared. But that's not the spring stretch. The spring stretch that we're calling x is equal to is equal to this length L minus its initial stretch, which was 0. Giving us our final stretch, square root of 0.75 squared plus 1 squared minus 0.75 squared. So take that number, throw it up in there, and we know how fast it is moving at 2. If we would have had some initial velocity, this term would not have been 0. We could have also had some initial spring stretch, so if we had a spring stretch, then this term would not be 0. Alright, I'm going to work on these and see how it goes.